You don't have to worry yourself about it. Our Lagbashel. Okay, here we are. Can you see my screen?
Yes, sir, we can see, sir.
Yes, sir.
So good afternoon, everybody. And I was
sir.
rushing from another class. I got here, I was expecting somebody to come. Your class rep is not a good class rep.
No, sir, maybe he's busy, sir.
Eh?
Maybe he was trying to send us the link, sir.
No. It's supposed to remind me.
Okay, sir.
So remember that we define what a system is as a quantity of matter or region in space choosing for study, or a space or quantity of matter that is of interest to us. We also define the surrounding, that the mass or region outside the system. We do define all those ones. The definition, okay, I'm actually looking like that class. Yes, my people are here so that I can pray for them to pass well. I'm in a class. Okay. Thank you. Okay, so when you come, I'll pray for you. They bring gifts to their teacher. Thank you. So boundary, we define the boundary as real or imaginary surface that separate the system from its surrounding. And we say boundary can be fixed and boundary can be flexible, movable boundary, fixed boundary. We also talk of system that may be considered as closed system, open system, isolated system. We have different types of system, and then system can also be under control. We talk about that. Then from there now we move to different type of properties. When we talk about the properties of a system, we are talking about properties that are measurable. So some familiar properties of a system can be your mass, can be your potential, can be your temperature, can be your volume, and so on and so forth. So properties also can be subdivided into intensive or extensive. Intensive or extensive property. So what is an intensive properties? The intensive properties are those properties that are independent of mass of a system. They are independent of mass of a system. Those properties are called intensive. And example of such a system is temperature, pressure, and so on and so forth, okay? Then extensive properties are those whose value depend on the size. It depends on the size. When you talk about size, you're talking about the magnitude, how big it is, the size of the system, the extent of the system. So they are. When you talk about that, you are talking about the extensive properties have mass, have volume, and so on and so forth. Intensive properties are temperature, pressure, and density, and so on and so forth. They all depend on one thing or the other. We can talk about another one in terms of volume per mass per volume, or mass per volume, depending on what you have. But just remember the definition. Then that takes us to what we call the total energy of a system. The total energy of a system is the sum of all the energies that are within the system that can coexist in the system. When you're talking about all the energies, we are talking about the thermal energy, mechanical energy, kinetic energy, electrical energy, magnetic energy, chemical energy, nuclear energy. And energy can also be subdivided into another form. We have what we call the spin energy, and then the energy that is as a result of vibrational energy, rotational energy of a system. If you want to look at it into details. So the energy all put together are what we call total energy of a system. So for system, okay, some of these energies may not have major effects on a system, of which you can say at a particular time, well, this energy is not of interest because the effect of the energy is not as much compared to the magnitude of other energies, okay? So, hello, somebody is putting it off again. Who is that? Your quantity off screen, no? Okay, don't off the screen, no, Joe. So for system, we typically dealt with in this course are some of the internal energy, kinetic and potential energy. In other words, the energies we'll be talking about in this course, or the energy that is of interest to us, are internal energy of a system, kinetic energy of a system, and potential energy of a system. So these three energies are of very important thing to us in thermodynamics, okay? So the total energy of a system now can be the sum of these three entities: kinetic energy, potential energy, and internal energy of a system. We all know the relationship between potential energy, the definition of potential energy, we all know it. The definition of kinetic energy, we all know that. So having said that, we will now try to talk about all other stuff, okay? Next slide. Yeah, I made mention of rotational energy and vibrational energy. When you have a molecule, yes, molecule can vibrate, it can rotate, it can go the other way. All these are under internal energy of a system, okay? So extensive property vary directly with the size, like I told you, volume and so on and so forth. The state of the energy. Now let's talk about state and thermodynamic equilibrium. A state of a system, that is system that is not undergoing any change. We have system that is not undergoing any change, static systems. All its properties of such a system are known, are not changing. They are not changing. If one property changes, then the state of that system changes. So in other words, it is the property of a system that determines the state of that system. It is the property of a system that determines the state of such a system, okay? Now, thermodynamic equilibrium. Equilibrium, it means state of balance. Equilibrium means state of balance. State of balance. A system is in equilibrium if it maintains its thermal state, if it maintains a constant thermal state. In other words, maintaining a thermal constant state implies having a constant temperature. The temperature does not change because the temperature is proportional to the energy. And variation in temperature is what can result into change of energy. So for a state to remain in state of equilibrium, the energy must remain constant. When we talk about the energy, if we talk about the thermal energy, temperature must not change. If we want to talk about the mechanical energy, the pressure must remain constant. And we can also talk about phase change. Changing from liquid to solid or solid to gas. That phase must also remain what? Constant. So that is what we mean by that. Then we talk about process. Process, that's another terminology. What is a process? When a system changes from one equilibrium state to another, it undergoes what we call process. So yes, transformation, the process of moving from one level to the other, okay? We have some processes that we can talk about. Isobaric process. Isobaric process is a process that occurs at constant pressure. Isobaric process is a process that occurs at constant pressure, at constant temperature, Isochloric process is a process that occurs at constant volume. Isochloric implies constant volume. So that is also a process. Isentropic process, constant entropy, constant entropy. Those are the different processes we talk about. In the exam, I can ask you to define the processes and give an example of that. And I can ask you to define what a process is. Give example of a process, okay? So path are series of states which a system passes through during a process. Yes, paths are series of states which a system passes through during a process. A system can go from one end to the other before getting to the final destination, and a system can decide to transit through A, B, C, D before getting to its final destination. Can be different paths. If you are going out of your compound, when you live in an open compound, you have different way you can get to your destination. So that's what we mean by paths, okay? So let's take them one by one now. When you want to compress a gas, and the gas is inside the cylinder, you know now you are talking about closed system. The system is closed. You apply pressure to it to compress it. Look at the process now. The temperature is constant, but the pressure and volume will change. The pressure and volume will change because you are decreasing the pressure. That results into compressing the system. And because you are compressing it, the rate at which the molecule inside the system collide with each other and the wall of the container increases. And you know that pressure is force per unit area. Pressure is force per unit area. So the rate at which they collude with each other and the wall of the container will also cause increase in pressure. So look at the process now. It moves from an initial state of a bigger volume. Yes, the person changing this must be a crazy guy. If I get him, you should remember it's called 0 in this course. If I get you changing all this, you will get 0 in this course. I promise you. I promise you. Messing up with the class. I promise you, you get a 0. It's a promise, so it's not bragging. No. Say that man is bragging. I'm not bragging. I'm promising you. And promise is a debt. So don't tamper with our system. If you don't want to take part in the class, you can decide to go. It's only 37, and whereas 36, 35 now, whereas we have more than that in the class. So take note of that. So a system remains practically in equilibrium at all times because a system wants to be in equilibrium. In other words, you want to be at a state whereby you don't need food and you are not overfed. Yes, our system wants to remain practically in equilibrium at all times. And so therefore, at that point, it is very easy to use equation of state that you can apply to that. And applying to that equation of state, excuse me, class, applying to that equation, hello, sir. Hello. it. So as I was saying, that system wants to remain in equilibrium at all time, it is easier to analyze any state, any system using equation of state. So work, we can do that. Work done by a system can be calculated. Yes, work produced by a system can be calculated, and work consumed or work input to a system, we can also calculate that with the help of equation of state. By the time we get to that, we will all see. We are still talking about different part of a system. Now look at this state now. This is another state. Remember, I made mention that a process is a series of connected processes that end in the same way. You can decide to go out through the door or go out through the window. You are still getting out of the place. So this is another process. And when you look at this process, it is in cycle to one. So when you look at the process, what happened between process 1 and 2? That is when you go, that is process A. When you look at process A, you discover it's higher, right? And the temperature is also higher. I'm sorry. At the final stage of A, the pressure is higher, the volume is lower. So when you have that kind of a process, it is called a process of compression. You are compressing the system. You are compressing the system because you are moving from a bigger volume to a lower volume, from a state of lower pressure to a higher pressure, compression. Then from 2, that is process B, to 1, to higher volume. In other words, lower volume corresponds to your large pressure. Large volume corresponds to lower pressure, and they arrive at the same. So that process is called expansion. Expansion. Okay? So there are so many ways of getting into that system. Okay? So now let's see the definition we have here. That's what we have discussed. We take us to the definition of our terms here. The first one, we have the first law of thermodynamics. The first law of thermodynamics contributes to the conservation of energy. Conservation of energy, when you talk about the conservation of energy, the total work done to a system must be equal to the heat generated plus the internal energy of that system. Remove yourself from video, Ria. Remove your video. Don't let me see your face. Remove your video, Ria. So for the energy, you know the definition of energy and how you can estimate or analyze the energy. We have microscopic energy and microscopic energy. If you are talking about the microscopic energy, you are talking about the energy of different entity. When you have water now, you can discuss water at the level of water molecule, and you can discuss water at the level of the hydrogen and oxygen, okay? Again, we have the microscopic energy. That is the energy that are related to the molecular structure of the system. And then we have macroscopic, MA, of the energy that are related to the motion that influence. So in that case, we are talking about the kinetic energy and potential energy of that system, all right? So what is the kinetic energy now? We define it as the energy of a process due to the motion of that process, and the formula is given as that potential energy due to the state of the height, the elevation of a system. In that case, both energies we talk about are macroscopic energies. Macroscopic. So the combination of these energies is internal energy, which is microscopic. Kinetic energy, macroscopic. potential energy in macroscopy, and that one will give you the total energy of the system. We have what we call the static energy also of the system and dynamic energy of the system, okay? So the static energy of the system will also be related. Work done, you can define what work done is, as is work performed by the system, and that can be calculated in terms of pressure, volume, and temperature. We'll consider that. When expansion, work done for expansion, work done for contraction, all those, we will discuss that. Each transfer in a system, all this energy must remain constant, okay? That is what the first law is talking about. Now, when you talk about each transfer, energy can cross the boundary of a closed system in two distinct forms. Energy can cross the boundary of a closed system in two distinct forms, which are through the process of what we call heat energy or work done. Heat energy is as a result of difference in temperature between 2 points of interest. So no heat transfer between two systems that are the same temperature. Water cannot flow between 2 points that have the same pressure. Water must flow from higher pressure to a lower pressure. The same thing, heat energy will flow from a state of higher temperature to a state of lower temperature. Take note of that. So we have 3 modes of energy transfer. You already know that. Let's think about the other terms now. Exothermic process is a process whereby heat is released to the surrounding. Exothermic process, don't forget, is a process whereby heat is released to the surrounding. Endothermic process is a process whereby heat is supplied to the system or the surrounding. Yes, a system that absorbs heat is called endothermic. Diathermic system was that permit heating of energy. Yes, the energy transfer through the wall alone. Okay, adiabatic, the walls that do not permit heating of energy. There's no energy that passes through that. So here we have now kinetic energy plus potential energy equals to the total energy U. And you can say that the change in the internal energy now, the Q equals to the Q plus the W plus that, where the W is expansion work done or work added to the system in form of electrical work. So if a system is kept at constant volume, the work done on expansion is 0 because the volume is not increasing or decreasing at constant volume, no work done. So when a system releases energy to the surrounding, the internal energy of the system decreases. So it is assigned negative. Take note of all this before we get into using the terminologies and using them to calculate whatsoever we want to calculate. Work is done by a system. Heat loss during heating process. When internal energy increases, we assign positive for increase in internal energy. And when can internal energy increase? When work is done on the system. When the system absorbs heat energy, those ones are positive, okay? For the negative one, heat is lost from the system or work is done by the system. They are assigned negative. So internal energy of a system now. Internal energy of a system is increased by transfer of either heat or work into the system. So a system has what we call internal energy. Okay, as you have your internal energy. If there's no food given to you, your energy cannot increase. And if there's no food drained from you, your energy cannot decrease. Okay, so for an internal energy to increase, you either do work into the energy, supply it into the system, or you transfer it into the system. So in that case, the change in internal energy of that system will be Q minus W, Q minus W. And that is what the first law of thermodynamics is saying, that the change in total internal energy of a system is the difference between the heat supply and the work done into the system, okay? So internal energy equals to heat added minus work done by the system. That is what that law is talking about. And those are the simple things you need to remember. Let's look at this example. A falling mass turning a pedal in an insulated beaker of water. In this schematic diagram, look at it. The moment you increase the mass, this paddle will roll through the pulley, and down we have the steerer. The steerer will miss the temperature within the content, okay? When you remove it from that, it will not. So mechanical energy is one that is doing work into the system, and the temperature keep on increasing, okay? So the apparatus for measuring the temperature increase produced as a result. Apparatus for measuring the temperature increase produced during the mechanical work done of a system. So if you add more heat, you see that the peddler will be moving and the molecules will be colliding with each other, resulting to increase in temperature of the system. That's an example of what we are talking about. This is another experiment you can do. You have a steam, and if the steam is coming out of your kettle and you have a fan, you can be allowed to move material from one point to the other. So therefore, steam issuing from the kettle makes pinwheel turn in this simple steam turbine. That is what happens in your turbine. As the heat is coming in form of vapor, it begins to roll. And as it's rolling it, the pulley will begin to roll. As it's rolling, the thread will begin to go around and lift the pin up. What can be done to lift a small mass up using that engine? That's a simple engine for you to see. And that is also what the first law is talking about. How about this? For your what do you call it now? Your car engine. It released by burning gasoline in the cylinder of an automobile engine causes the piston to move, converting some of the heat to work. Look at it now. So the gasoline is allowed in and the spark plug is burning it. So by the time it's burning, you see the piston moving up and down. So work is done. So the heat is converted to work done by moving the piston up and down, and that is the process in your automobile. The process in your automobile. The process in your automobile. So the internal energy, that is another way now. The internal energy of a system is increased by the transfer of either heat or work done into the system. In other words, if you want to increase the internal energy of a system, do work into the system or supply it into the system, okay? So that is what the first law is talking about. How about the zeroth law of thermodynamics? Two objects in thermal equilibrium have the same temperature. That's another way of stating it. Two objects in thermal equilibrium have the same temperature. Two objects in thermal equilibrium have the same temperature. That is the zeroth law, okay? And we can also define it in another way. If A and B are in thermal equilibrium, if A and B are in thermal equilibrium, and C is in thermal equilibrium with A. Automatically, C will be in thermal equilibrium with B. I take it again. If A and B are in thermal equilibrium, and A is in thermal equilibrium with C, automatically C will be in thermal equilibrium with B. Okay, that's another way of stating this zeroth law. But two objects in thermal equilibrium have the same temperature. They have the same temperature. So what is internal energy now? The internal energy of the system is the sum of kinetic energy and potential energy of the atoms and molecule making up the system. The sum of kinetic and potential energies of the atom or molecule making up the system, okay? We already defined it. Emphasis on the first law of thermodynamics. The increase in the internal energy of a system is equal to the amount of heat added to the system plus the amount of work done on the system. Another way to state that law. The first law states that increase in the internal energy of a system is equal to the amount of heat added to the system plus the amount of work done on the system. That is the summary of the noise I've been making so far. Another way of explaining that law again, you can also state that the increase in internal energy of a system is equal to the amount of heat added to the system minus the amount of work done by the system. Remember the work on or by. Don't confuse it, on or by. These two statements are correct and are acceptable at any level. But remember what the content is. So change in internal energy equals to heat added minus work done by the system, minus work done by the system. And you can write it out in this form and define your terminology. State first law of thermodynamic equilibrium. You can write out this equation and explain each term. That change in increase, you can put it as increase in internal energy of a system, the delta Q, Q delta U. Q equals to heat added to the system, and W, work done by the system. Don't forget there are definitions. When they ask you to define, any of the three is acceptable. The third one, you must explain all the terms you put in the question, okay? Okay, so let's look at this now. Previously, I was talking about isobaric process, isochromic process, yes, sorry, baric process. Now, I talk about isothermal. I talk about isochromic. Let's look at this system and see how work is done by the system. We have a piston and we have gas inside the piston. This type of a system is a closed system. You can decide to move the piston up and down as you are looking at it. So if the piston is at point A before, where you have the dotted line, can you see the dotted line, class? Can you see the dotted line?
Yes, sir.
Yes, that is the original place of the piston. That means the molecules inside the cylinder have more rooms to move about before they collide with each other or the wall of the container. The moment you move the piston downward by reducing the volume by delta T, by delta V, that means you have moved a distance of D along the cylinder, okay? Now, what you have done is to reduce the volume of the cylinder. Reducing the volume of the cylinder, you are compressing the molecules together, thereby reducing the space at which they can interact with each other. So they don't have to travel a longer distance before they collide with each other. And the collisions of the molecules together and with the wall of the container is what produces the pressure within the system, okay? So the pressure will increase. So let's look at it now. We said work done is equal to force times distance. You remember that? Work done equals to force times distance. But here, we have force that is applied to the piston to reduce the volume down. Then we can calculate the area with which the piston have moved because we know the length and breadth of that space. So length and breadth will give you the area, okay? So we know that if you multiply pressure by area and divide by area, you have not done anything, right? If you multiply the force, you see, by area and divide by area, you have not done anything. Am I correct?
Yes, sir.
They don't know. Divide pressure by area, and multiply by area. What do you get? You still get your force back, right?
Yes, you still get force times distance.
But what we want to show here is that force per unit area is what we call pressure. Okay?
Yes, sir.
And the distance D multiplied by the area you are multiplying by it is what we call the volume. Area is length times breadth. Then times D, which is the height, that gives you volume, right?
Yes, sir.
And it's the volume that is changing. So
yes,
work done here will be pressure times change in volume.
Yes.
That is how we collect this together, okay?
Yes, sir.
We have not done anything wrong with this formula. This is how you can calculate the work done by a movable pressure. By a movable pressure. I'm supposed to insert a work example here, but I have not done that. It's my fault. It's my fault. So I will try to see what I can do about that, okay?
Yes, sir. No problem, sir.
Have I given you assignment before?
No, sir.
No, sir.
That is too bad. Assignment. I've not given you assignment.
Yes, sir. No, sir.
Okay, I will give you assignment. I'm coming.
Yes,
Homework here. Then homework here again. Homework here. Okay. So I've noted it down. I'll give you the assignment. And have I sent you the note?
No, sir. No, sir.
No, sir.
I'm going to send you notes to all this. Okay?
Yes, sir.
Akinola is showing the tattoo of a... What kind of tattoo is this?
No, a tattoo,
is that the court you belong to? What is it?
Anime.
It's not an artwork, sir.
It's an artwork.
Artwork, sir. Isn't it like a...
It's an artwork. Okay, I thought it's a tattoo of where you belong to. Maybe you just want to show us. All right. Okay, let's move ahead now. How many of us in class now? Class rep?
37 altogether, sir. But some...
Okay. But we're supposed to be more than that.
Yes, sir. Someone having issue with the login and they are being logged out by the network, sir.
They logged them out?
Yeah, the network.
Yes, sir. Yes, sir.
I don't really understand. Why is it that they cannot get to the class?
Like they already knew before, like four of my
some people were unable to log out.
Been logged out.
Okay, the system locked them out.
Yes, sir. So they are trying to reconnect.
Okay, maybe they are doing something that is wrong. All right, so we are going to do a lot of calculation under this and all the talk I've been doing before. Let's go forward. So what is a heat engine? What is a heat engine? A heat engine is a system that supplies heat to a reservoir, and the heat, during the process of supplying heat to the reservoir, work is also done. So here is the demonstrator. We have the hot reservoir represented by TH, hot temperature, I heat, QH, higher heat, QH, W work done to the surrounding, QC, that is the temperature of the reservoir or cold temperature. TC, yes, cold temperature. Okay, Q represent heat, T represent temperature. Okay, temperature. If the heat is hot, the temperature will be hot. If I heat, high temperature. Low heat, low temperature. Cold heat, cold temperature. Okay, note that. So thermal heat, QH, is introduced to the machine. Some of this heat introduced to the machine is converted to mechanical work, W, and some of the heat released into the surrounding at a lower temperature. Some of the heat is released to the surrounding at a lower temperature. At a lower temperature. So you understand the scenario now?
Yes, sir.
Okay, so we can move ahead. By the time I use QH, QC, W, it should not be a strange thing to anybody in the class. And that's why I'm taking my time gradually to let you know. By the time I use some terminology like process, path, or this and that, that should not be new to anybody in the class also. Because we are not rushing, we are going gradually. So what does the first law tell us about the heat engine? The first law is telling us that delta Q equals to delta U equals to Q minus W. You remember that? And we say delta Q, sorry, delta U is the change in internal energy of the system.
Yes, sir.
Q is the heat supplied to the system.
Okay.
W is the work done by the system, right?
Yes, sir.
So the Q here is the difference between the hot heat supply and the cold heat supply. That is why you have QH minus QC. Are you okay now?
Yes, sir. Minus the work done too.
Look at it. This heat is supplied to this engine here.
Yes.
The heat here now will be QH minus the one that has been supplied to the reservoir.
Yes, sir.
All right. Minus the W now. That will give us delta U. So the internal energy of the engine does not change from the circuit to circuit. The internal energy of the engine remains constant. Delta U equals to 0. Hence, Q equals to W. Work done to the system equals to the work supplied to the system. Are you okay now? Because
yes, sir.
The internal energy does not change at any circuit of the system. So the net heat flowing into the engine equals to the work done by the engine. The net heat flow into the engine equals to the work done by the system, by the engine. So work done by the engine equals to QH, that is heat from hot region, minus QC, heat going to the cool region. That's how we get that. So therefore, if I substitute W back there, you see that my delta Q remains 0, right?
Yes, sir.
Okay. So by the time we have assignment and solving problem, you will see what I'm talking about. So let's go to the second law now. Am I rushing?
No, sir.
Am I rushing you?
No, sir. No, sir.
Okay, thank you. So the second law of thermodynamics, that is what we call the Carnot engine. So the Carnot engine is an ideal system which turns out to have maximum possible efficiency. Carnot engine is an ideal system which turns out to have maximum possible efficiency. And that efficiency of a machine is what is of interest to us. Let's look at the diagram and treat it one by one. By the time we treat it one by one, we go to schematic diagram and then we go to sketching again. Okay, let's look at it. The first process that we have is that heat is supplied into the system, QH into the system, and because it is supplied to the system, there is enough pressure to move the volume up. So because the temperature remains constant, we call it isothermal expansion. Isothermal expansion. The word isothermal implies a process that the temperature remains constant throughout. Isothermal process, isothermal expansion. So here, what causes expansion, like I said, is the result of pressure that changes. The second one is adiabatic expansion. Here, there is no supply of heat nor temperature, okay? Yes. The third process is when the compression happens, when you compress the system at a constant temperature, and we refer to that as isothermal compression. And we also have adiabatic compression also. So let's take it now. If TH temperature is the hottest temperature in the engine, and TC is the temperature outside the engine. Remember, the unit have to be in Kelvin. The unit have to be in Kelvin. If you are given the unit of your temperature in Celsius, you're going to, what are you going to, how do you convert it to Kelvin now?
Plus 273.
Thank you, Adebayo. And Adebayo, are you the class rep?
Yes, sir.
Okay,
For
keep the record.
education.
For physics education.
Yes, sir.
Okay, are you always present?
Yes, sir.
Okay, if that is true, keep record of this. Give yourself 1 point. Adebayo 1 point. So as we are going, people that participate in discussion, you'll be noting them down. I will call their name, you record 1 point or half point or 2 points, depending on the level of their contribution.
Yes, sir.
So
thank you, sir.
You have to convert to Kelvin. Adebayo have already told us that we're going to add 200 and what? 273. Yes, to your Celsius to get Kelvin. So to be able to calculate the efficiency now, efficiency is work done, all over work, the work supply. That will be W all over QH. And since we are able to prove that the W equals to TH minus TC and Q equals to T. So our efficiency can be the difference between the hot and cold temperature divided by the hot temperature. Definitely it's going to be a fraction, and you can convert it to percentage as you want it. This shows that it is not possible to have an efficiency of 100%.
Yes, sir.
That is the reason. It shows that it is not possible to have an efficiency of 100%, you always lose some energy into heating of the environment. So in an exam, I may ask you to calculate efficiency and give me reason for why you cannot get 100%. For a system that involves heat transfer from one place to the other, you know that the surrounding will absorb some heat. And for a system that requires one body moving against the other, work must be done against friction, and so on and so forth. You should know why some of the heat, some of the work done is being lost in form of heat energy. Okay?
Yes, sir.
Somebody is messing up with our work. Who is the fellow? Elijah, are you? Yes, it must be Elijah, I know. But if I'm annoyed with you, you will not laugh. Because you are disturbing the class now. If I take you up, it's suspension. Oh. Yes, and you'll be begging, and it will be too late. That is why I don't like causing trouble. But if I start the trouble with you, I normally make sure I see the end of that trouble. I don't do trouble halfway, like Yoruba people used to do, and be begging. No. Don't even start trouble you cannot finish. If I start trouble with you, I must finish it too. So please, don't let us enter trouble with each other, okay? I'm begging now. If there's any issue, let us know and settle it amicably. But because you are using one thing or the other to disturb me now, it becomes another problem with me, okay? So please. What am I talking about now? I'm talking about something else. Okay, energy wasted. Okay, idealized thermodynamic circuit, I said, consists of 4 reversible processes. When you say reversible process, it's a process that can go around and you can still turn it around, okay? And we can apply any fluid. Any fluid can be, it can be used. When you say fluid, it can be gas or liquid, okay? So the first steps for a Carnot heat engine are, the first step we have is heat is supplied to the system at constant temperature. But the temperature now is high. The temperature does not change. Maybe if it is 15,000 degrees Kelvin, it remains 15,000. It does not change. But what will happen, because of the fact that you have increased the temperature, what you have done is that you have energized the molecules of the fluid. You have energized the molecules of the fluid within the compartment. And because you have given them energy, they have ability to move up and down, to collide with each other, collide with the wall of the container, and generate pressure. And this pressure will move the piston up. Moving the piston up means work is done. That is circuit 1 to 2. And because the temperature remains constant, the volume of the container increase. We call it reversible isothermal expansion. TH remains constant. It does not matter the value of TH, but it must be an outer value. Are we okay with that? The second process, which is 2 to 3, because of the fact that the molecule have attained certain level, no energy, no heat supply, no heat exchange, then from there is reversible adiabatic expansion. The internal energy does not change, whereas the temperature changes from hot to cold as you go. So because it is cooling down, the rate at which the molecules of the fluid or atom of the fluid collide decreases. The piston will go down at a cold temperature, which we call reversible isothermal compression, process 3 to 4 at cold temperature, lower temperature. That TL is a lower temperature, TH higher temperature. So they remain constant. And the last one, which is 4 to 1, getting back to its initial stage, the internal energy of the system does not change because of the temperature, and the whole process continue on and on like that. This has been explained using what you can visualize. We are now taking it to a classroom setting. What I've explained here, taking it to a classroom setting, and here we are now to a classroom setting. Here we are. So what I've explained now, you can see it. Here we are. The process starts from 1 to 2. Look at the pressure here. But the temperature remains constant. The temperature remains constant. Okay?
Yes, sir.
And at that constant temperature now, there's what we call compression. Sorry, that's what we call expansion, because we are moving the volume here. Look at it at this point. You see my arrow moving?
Yes, sir.
Are you able to see my arrow?
Yes, sir. On the
Yes, sir.
X-axis.
Okay, very good. When you look at this point down here, this is a lower pressure and a lower volume. And when you look at where it is in number 2, it's higher volume, right?
Yes, sir.
And that is expansion, thermal expansion. So 1 to 2. And by the time it goes to between that process, bends. Okay, hold on, class. Hold on, class. Hello, class.
Hello, sir.
Hello, class. Yes. This class was supposed to take place when now? When did we supposed to take this class? Which day? This is 201.
I think on Monday, sir.
201, Abi. Hello? Adebayo?
Yes, sir.
It's supposed to be
Yes,
Monday
sir.
class. Monday class.
Yes, sir. Monday class. Yes, sir.
In the morning.
Yes, Monday and today. Yes, sir.
No. It's 2 hours. It's only 2 hours. Monday, 2 hours. 8 to 10, I think. That's what HOD was saying, no. That it's me that is not allowing you to come to class. So on Monday, everybody come to class. So I will take attendance and possibly give you test. Say I should give you a little test. I believe everybody, 33 of you is hearing. That's why I moved it.
Sir? Yes, sir. Yes, sir.
Yes, sir.
That's why I moved it to HOD just come. Okay, set school has resumed. Now, let's continue with what we are talking about here. So from process 2 to 1, you will see that we are moving at what now? It is adiabatic process, adiabatic compression. From there, moving from low pressure to a low volume to high volume. Then from 3 to 4, you see it now? That becomes isothermal process, moving from higher volume to lower volume, isothermal compression, okay? And the whole cycle continue just like that, 1 to 2, 2 to 3, and so on and so forth. Now, let's take them one by one and see what is going on here. In process 1 to 2, let's look at it. Work done by the gas is equal to the sum of the product of change in volume. That is the integral of V P dV. P dV. That is to say, area under the process curve 1, 2, 3. Area under the process curve 1, 2, 3. And when you look at it, the V is greater than 0 from 1, 2, 3. So the work done is greater than 0. Are we okay with that? Now,
yes, sir.
When we come to the next one, under this, under 1, 2, 3, let's take 3, 2, 1 now. Work done by gas is the area under this curve that you can see here. So area under the curve 3, 4, 1 is less than 0. It's less than 0. So when you take the integral of that, it's less than 0. So to calculate the net work done now, we can put that together. So the net work done, 1 to 2, 2 to 3, and 3 to 4, back to 1, is the area under the parallelogram you can see here. You can call it rhombus or whatever you call it, but it looks like that exactly. Okay, so don't forget about that. Now, the text from here. The efficiency of an irreversible real heat engine is always less than 1. The efficiency of irreversible real engine is always less than 1 and less than the efficiency of a reversible operating between the same two reservoirs. In other words, the efficiency of a reversible engine is always greater than the efficiency of a non-reversible engine, both of them operating under the same system, okay?
Yes, sir.
Another point to take home is that the efficiency of all reversible heat engines operating between the same two thermal reservoirs are the same. The efficiency of all the reversible heat engines operating under the same two thermal reservoirs are the same. So they have the same efficiency. That's another point we can take from our explanation previously. However, both of the statement above, which that is to say, the reversible is less in efficiency compared to reversible, that's irreversible is less to reversible, and the efficiency of reversible engine operating in the same thermal condition are the same thing, demonstrate the fact that second law, it demonstrates the second law of thermodynamics. It demonstrates the second law of thermodynamics. Therefore, Carnot engine defines maximum efficiency of any practical engine. Yes, it defines that. So thermal efficiency equals to work done all over the earth heat. And you can calculate that, substitute, and you get what you want. Just work over Q equals to 1 minus QE over this. In other words, supply what W is. W is QH minus QC. Am I correct? If you put that one there, play around with the figure, you get this. So therefore, the relationship is often called Carnot efficiency. Carnot efficiency. And finally, for today, I'm coming up. Yes, finally for today, this is where we are stopping today now. Finally for today, when you look at the efficiency of the Carnot engine, you see that you can calculate it in various forms. One, if you calculate the process from 1 to 2, as you have seen it in the diagram, that is isothermal expansion. Delta U equals to 0. And then for the earth, it equals to Q between 1 and 2, which is equal to W, work done between 1 and 2, which is the integral of PdV. Substitute the necessary equation of state there, because you know that PV equals to what? PV equals to what? nRT. Remember that?
Yes, sir.
So when you substitute that, what you have is mRT in log of V2 over V1. From the other process again, because it is adiabatic, no heat is supplied to the system. T, the ratio of low temperature to high temperature is same thing as V2 all over V1 raised to a constant minus 1. And that constant is called molar gas constant, okay? So you can do the same thing again to the other process, and then to the adiabatic process. So from 2 to 4, you have change in volume to that, and that becomes equal. And since in log V2 over V1 is equal to minus in log, when you put everything together, you have QL all over QT equals to LT over that. So at the end of the day, the efficiency is 1 minus this QL all over QH. So we can do that. And I'm going to leave you here. We're going to stop here today. Why? Because that is the appropriate point to stop, so that I will not start another thing next time. All right. Okay.